The half-life is the time needed for 1/2 of a radioactive sample to decay into something else. For example, carbon-14, which has a half-life of 5,730 years, it decays into stable nitrogen-14 via beta decay. You might remember that when we talked about beta decay, we talked about how you go up one element on the periodic table. Well, carbon is number 6, nitrogen is number 7, so we've gone up one number. And in beta decay, since beta particles are electrons, essentially, electrons have almost no mass, so you can see that the mass has remained the same, 14 for carbon, 14 for nitrogen. In any case, whenever you're doing half-life calculations, what you do is you take your radioactive sample, so this black rectangle indicates a radioactive sample, and after one half-life has passed, half of that sample is no longer radioactive. The other half still is. Then, when another half-life passes, we don't simply drop down to no more radioactive material. We drop down to half of this. Watch the screen. After another half-life passes, half of that has turned into something else. After another half-life passes, half of that, half of that. We keep cutting in half every half-life. Incidentally, carbon-14, which you might have heard of radiocarbon dating, we can find out how old certain bones are. You can see here at the bottom, it's only useful for dating objects that are about 100,000 years old. So it's not going to work for the dinosaurs because they went extinct some 65 million years ago, plus or minus, and so we have to use other radioactive isotopes to figure out how long ago dinosaurs were around. So let's take an example. Let's say that we have 120 grams of carbon-14. So when we start, you can see in the table we have 120 grams of carbon-14 and none of it has decayed. So we have 0 grams of nitrogen-14. So I'm going to represent that in the upper right corner. The red indicates carbon-14 and the light blue will indicate nitrogen-14. You can see that in the picture right now we have no nitrogen-14. So after one half-life passes, that would be 5,730 years, half of the carbon-14 has decayed into nitrogen-14. So you can see in the picture in the upper right that now we have half carbon-14 and half nitrogen-14, which means in the table we have 60 grams of each. See, the total mass is going to stay the same. So we started with 120 total grams. We need to still have 120 grams, but it's not all carbon anymore. Half of it is nitrogen. Then another half-life passes. In other words, this is 5,730 years more than where we were right here. Well, when another half-life passes, half of the radioactive sample is no longer. So we go from 60 to 30. If you watch the picture in the upper right, we now have only half of that radioactive, which means how many grams of nitrogen-14 do we have? 90 now. The total mass, you see, is still staying the same. After another half-life passes, this is 17,190 years from now, we only have 15 grams of radioactive carbon-14, and we're going to watch some of this red disappear from the picture. Namely, half of that red that was there is now gone. The total mass of nitrogen-14, you can see in the picture that we are getting more and more and more light blue every time. So now we have 105 grams of nitrogen-14 because, again, the sum of those has to remain 120. If another half-life passes, the 15 grams will drop to 7.5 grams of carbon-14, and half of this red is about to disappear. There it goes. That is now nitrogen 14, 112.5 grams of it. And we could continue the table, cutting the 7.5 in half, cutting the next thing in half, in half, in half. You can see why 65 million years from now we would have virtually no carbon-14, certainly not enough to measure. Alright, let's use this graph to determine the half-life. So what we can see here is that we've got number of counts per second. You might think of it as number of beta particles emitted from a sample in a given second. And when we tune in, we're getting about 80 counts per second, roughly. Well, what does the half-life mean? The half-life would mean that we only have an amount of material that would emit half of that. So 40 counts per second. So let's go down here and find 40 counts. How many days have passed before we drop from 80 counts per second to 40 counts per second? 40, 40, and that would be day number 6. In 6 days, we've dropped from 80 counts per second to half of that, 40 counts per second. That's the half-life. Let's continue that. Let's say, okay, here, at 40 counts per second, we're at day number 6. What's half of 40? Well, 20. Okay, what day are we on when we're down 20 counts per second? Hey, that's day 12. Wait a minute. Day 6 to day 12, that's 6 days also. So the half-life is about 6 days. We can read that right from the graph.